So in this task, we're going to visualize and identify the sp and d shell atomic orbitals of the krypton atom. So again, we start from our home screen. We select the WebMO app with the icon at the bottom in the middle of the screen. And here, instead of creating a krypton atom from scratch, we're going to load the results of our previous simulation that we performed on the electronic structure of the krypton atom. So from the menu on the bottom, we select the option on the right hand side, the WebMO option. And now from the options at the top, we select Job Manager. So we have a series of simulations that we run previously. The one that we're interested in is this one, krypton, at the very top of that list. So it's named KR. We select that. And that loads the results from our previous simulation. So here what we're particularly interested in is the atomic orbitals. Now this piece of software usually concerns itself with molecules rather than atoms, so it doesn't list atomic orbitals explicitly, but where it lists molecular orbitals, in the case of an atom, they are our atomic orbitals. So we select results. And we've got an option down at the bottom, molecular orbitals. We select that, and we have a list of orbitals. Now, here only been given some of those orbitals with energies greater than a certain threshold. We see there's a box that says energy and says greater than minus 1.38419. If we just clear that option from that box, we see all of the atomic orbitals of the krypton atom. Now you may know what the electronic configuration of the krypton atom is, but if you don't, well, it has an argon core, and then the valence electronic configuration is 3d10, 4s2, 4p6. So there are 6 4p electrons, 2 4s electrons, and 10 3d electrons. And you may know that each atomic orbital can be occupied by a maximum of 2 electrons. So that means we'd expect to find 1 occupied s orbital, 3 occupied p orbitals, and 5 occupied d orbitals. And because we just have an atom here, we'd expect all of the p orbitals to have the same energy, all of the d orbitals to have the same energy. Now, we can have a total of 3 different p orbitals, our px, py, and pz orbitals, and a total of 5 d orbitals, but we only have a single s orbital. So what we'd expect if we considered the occupied atomic orbitals of the krypton atom, we'd expect to have some orbitals that have their own individual energy. We'd expect to have a set of 3 orbitals that had the same energy. We'd expect those to be the p orbitals, and a set of 5 orbitals that would have the same energy, which we'd expect to be the d orbitals. So if we look through the orbitals we've calculated using WebMO, then we see we have a whole list here. In total, we have 43 atomic orbitals. We're interested in the occupied orbitals. And so you see one of the columns of data here is labeled occupancy, and we see those orbitals that have an occupancy of 2. That means they're occupied by 2 electrons. And since we're interested in the valence atomic orbitals here, we're looking for the highest energy orbitals, because the lower energy orbitals are the core orbitals of the atom. And it's the valence atomic orbitals which are responsible for the chemical properties of an atom. So if we scroll down, we find when we get to 18, then we have an orbital with occupancy of 2, but when we go to orbital 19, we have an orbital occupancy of 0. We call those virtual orbitals. So we're only going to consider those orbitals 18 and below. And if we look at the energy of those orbitals, well, we find that orbitals 16, 17, and 18 have the same energy, an energy of minus 0.38419 Hartrees, where orbital 15 has an energy of minus 0.89091 Hartree, and then orbitals 10 to 14 all had the same energy, minus 3.23573 Hartrees. And that fits in with what we were talking about, the electronic configuration of the krypton atom. We've got 5 orbitals all with the same energy, which we would identify as being the d orbitals, 1 orbital with a unique energy, which we would associate with the s orbital, the 4s atomic orbital, and then 3 orbitals with the same energy, which we'd associate with the 4p atomic orbitals. So we can see if that's correct. We'll first look at the s orbital, or what we think is the s orbital. That's orbital number 15. So if we go to row 15 in this data, and you see there's a magnifying glass towards the right hand side, if we just tap that magnifying glass, then we get this picture, and we can rotate this atom around, but it doesn't change, and that's because this orbital that we visualized here has spherical symmetry, and that's characteristic of an s orbital. An s orbital is spherically symmetric, so it just looks like a ball surrounding the nucleus, and that's what we see here. Okay, so we've identified our s orbital. If we go back to our results, well, we can now think about orbitals 16 to 18, those 3 orbitals with the same energy, which we think will be our set of 4 p orbitals. And our p orbitals are different to our s orbitals. The p orbitals are characterized by 2 lobes, one of which corresponds to the orbital being positive, one of which corresponds to the orbital being negative. And the 2 lobes are separated by what we call a nodal plane. So let's visualize each of those in turn. We'll have a look at orbital 16. Well, from that view, it looks apparently exactly the same as the s orbital. It appears to be spherical, but that's just because of the direction we're looking at the orbital. If we rotate our atom, we actually find that this orbital is comprised of 2 lobes. There's a lobe in red and a lobe in blue, and the blue lobe corresponds to values of the atomic orbital that are positive, and the red lobe to values of the atomic orbital that are negative. And that area in the middle, which separates those 2 lobes, defines the nodal plane. And p orbitals are always characterized by a single nodal plane. So this is one of our p orbitals. We can go and have a look at the other p orbitals. So, for example, orbital 17. So it looks like that same orbital, but it's just rotated by pi over 2 radians, or 90 degrees. So still a positive lobe, a negative lobe, and a nodal plane between the 2. And then finally, we can go back to our results and look at orbital 18. And we see, again, this is a p orbital with a positive lobe and a negative lobe. And if we looked at those 3 p orbitals at the same time, we'd see the lobes were pointed in different directions, either in the x, the y, or the z directions. We label these 3 p orbitals the px, the py, and the pz orbitals. We can label the d orbitals as well, but it's a bit more complicated. But the d orbitals are typically characterized as having 4 lobes, although there is one of the d orbitals that only has 3 lobes, but they're always characterized by having 2 nodal planes. So we've identified our s and our p orbitals. Now we can go and have a look at our d orbitals. So they are orbitals 10 to 14, or at least that's what we're expecting. We'll have a look at orbital 14 first. So first thing to notice, those d orbitals are more compact. They take up less space. That means the electrons occupying those orbitals are more tightly bound to the nucleus of the atom. And that actually correlates with the energy of those orbitals. If you look at those energies, these orbitals have a lower energy than the s and the p orbitals, and that corresponds to the d orbitals being more stable in the argon atom. In the krypton atom. Here we can see the 2 nodal planes. Well, first we can see the 4 lobes. We've got 2 positive lobes and 2 negative lobes. And you can see they're separated by these nodal planes, and the nodal planes are perpendicular to each other. So if you imagine 2 planes coming out of the screen, one horizontal and one vertical, that would give you the nodal planes for this atomic orbital. So we can characterize that as a d orbital. If we now look at orbital 13, it looks similar, just rotated again by pi over 2 radians, but you can see those 2 nodal planes and the 4 lobes. We can do the same with orbital 12. Similar thing, 4 nodal planes, 4 lobes and 2 nodal planes. Orbital 11, well, that's the one that looks a little different. It does have 2 nodal planes, but actually they're not nodal planes, they're nodal surfaces, but they're actually conical. So there's a conical surface separating the red lobe from the blue lobe, and another one separating the other red lobe from the blue lobe. But this d orbital we can characterize as having these 2 lobes where the orbital is negative, and then this annular lobe around the equatorial region of the atom where the orbital is positive. So it looks a little different to the others, but it is one of the d orbitals. And then finally we've got the final d orbital, which looks more familiar to the other 3, where we have the 4 lobes and the 2 nodal planes. So that identifies the 4s, the 4p and the 3d orbitals in the krypton atom.